All right, so in Chapter 7 is what we're looking at in our Stewart textbook there. The red Stewart text is in Chapter 7. We're going to take a look at trigonometric functions and their derivatives. So what I want you to do is I want you to draw a little sketch of the sine function. So I'm not sure how much you remember with the sine function. Hopefully you should remember a lot about it. One period of the sine function, what is the period length of y equals sine theta? Remember that? What's the period length? 2 pi. Exactly. Okay, so we're going to go pi here and 2 pi right here. So in my graph paper I've counted 8 squares for this. Now let's go back into the negative direction as well. 1, 2, 3, right back to there. Negative pi. It's a bit tight, but okay, so what we're going to do is we're going to sketch a period and a half of y equals sine theta. All right? And we know, or you should remember, that sine theta, sine of 0 is 0. Okay? Now, how are we going to know these values? Do you remember this little thing that we studied called the unit circle? You guys remember that? From pre-cal 30? The unit circle. So we have this little circle here, and the coordinates of the circle here are 1, 0, right? And the coordinates here are 0, 1. Coordinates here are negative 1, 0, and 0, negative 1, correct? So we did also have some important coordinates in the first quadrant that we memorized. Do you remember what this one is? That this theta is pi over 4, or 45 degrees. Remember what this one is? Root 2 over 2, and the second coordinate is the same, right? You guys remember this? Is it coming back? Ringing a bell? Do you also remember that this was the cos value of pi over 4, and this was the sine value? And we also had a third one in there too that was the tan value. Do you remember that? And of course this will be 1, because tan is sine divided by cos. So these ones here you might remember, and of course there's some similarities to all of the angles that have a reference angle of pi over 4, or 45 as well. Same numbers, just in different signs. Okay? So this would be good to remember, and that goes all the way around. The other ones that we want to remember, and seeing as we're graphing sine, why don't we talk about sine again? So let me just blow this up for you. That's at 45 degrees. Now where's 45 degrees on our little chart over here? Well, if here's pi, this is going to be pi over 2, which is 90 degrees. And theta equals pi over 4 is 45. So here's pi over 4. Now this isn't a lesson about graphing sine theta, but I do want to take a few minutes here just to make sure that we're on the same page here. So root 2 over 2 is the x value, or the theta value, which this is theta right here. Okay, the x kind of coordinate here. And then this y value is just the second number. So root 2 over 2, let's say this is 1. So root 2 over 2 is, I think, about 0.86 or so. So it's up around here. Okay. Now 0, theta equals 0, the point is 1, 0. So what do we have for a y value? Right here. Okay, 1, 0. So what does that mean? That means the cos is 1, and the sine of theta equals 0 is 0. So that's why we start here with the sine. Okay, so I initially put this point, and I'm thinking, oh, do you remember why sine of theta is 0? So we go back to the unit circle. Okay. Now what about pi over 2? So here's pi over 4. What about pi over 2? What's the coordinate there in the unit circle? 0, 1. So again, this is the sine, the second one. So guess what? Our value here is 1. So the sine pi over 2 equals 1. we've also got this so far. Sine of pi over 4 is root 2 over 2, which on your calculator, if you get that going, okay, the square root of 2 divided by 2 is, oh, my bad, I said 0.8. I said 0.86, that's my bad, 0.707. So you get 0.707 there. I guess that's, oh, yeah, my mistake, root pi over 3. I guess that must be the root 862. Anyways, yeah, 0.707. All right. Now, as we move along, okay, pi is halfway around here. And so what's the coordinates there? This is cos, this is sine. So what's the sine of pi? 0. You guys remembering this? Is this ringing a bell? All right. Okay, so I'm going to quickly fill out the rest here. All right. 3 pi over 2 is negative 1. And so on. 2 pi is 0. And we've got these values 0.707 in the negative direction here. All right. So if we kind of fill these in really quickly here with a different color, let's use green. Then we have the sine, looks like this. Like that. And of course, if we're going the other direction as well, the other half of it kind of looks like this. Right? All right. So yeah, here would be that 0.86. Okay, so what about the derivative now? We're talking about derivatives of trig functions, right? So do you remember way back we used to, we graphed the derivative of a function? And what we're going to do is we're going to do that for sine theta. So I'm going to do this. Underneath I'm going to draw another axis, okay? And everything is going to be the same here. All these are going to be the same. So we're going to use the same sort of reference points. And for the derivative, so this is y prime, right, of sine of theta. So this is y, and this is going to be y prime. We're going to graph it. So if do you remember how to do that? Do you remember where we start there? Do you remember what sort of things we do? Okay, the zeros. Now, the zeros, and remember we're doing the derivative. So the derivative represents the slope of tangent lines, right? So where is the derivative 0? Well, looks like over here the derivative is 0. And so because the slope of this tangent line here is 0, we drop straight down and we plot y equals 0. Good, we have zeros over here as well. So there's a 0 at pi over 2. There's a 0 here, and so on. Okay. All right. Well, that's pretty good. This is a little bit tougher for us to imagine, but if we had a derivative or a tangent line right here at y equals 0, it would look something like this, right? And what slope do you think that would be at? Now we could do a crude measurement here. That's sort of more like it, and sort of more like it there. All right. And if we actually measured the measured this, what would it look like? That looks like well, a rise of 2 and a run of a little less than 1, or somewhere around 1. So that's looks like a slope of about 2. But I wonder how accurate my tangent line is. You know what we're going to do? Let's do this. Let's graph. And if you have your graphing calculator, you can grab one if you need to right now. But I'm going to graph sine theta. Okay, I'm going to adjust my window a little bit here too. Make sure your calculator is in radians, okay, when you do this, because all of these x values for theta are going to be in radians when we're talking about trig functions, right? That's why radians exist, because it's much easier to talk about the trig in radians. Mode. Hit mode. You should have this screen, so just go down, highlight radians, click on it. So now if we graph, now we see the sine coming up. And I'm going to adjust those windows here for you. Alright, so there I've adjusted those Windows settings with you, and I've got a graph that looks very similar to what we put over here, right? So let's now graph what this line would be and see if we can get a tangent here. So for example, we said this is about a slope of, up to and over, maybe 0.8, right? So a rise of 2, a run of 0.8. What's 2 divided by 0.8? You know? 245? 2, well, I tell you what, let's do this. If you don't know that, you can do that on your calculator, that's fine. Or you could just go like this. We're going to do this line, right? So y equals mx plus b, right? So what is m? Well, we said it's 2 up to divided by 0.8. So if you don't know that, you could just put it right in your calculator right there. And that's the m value, x. And then the b is 0, 0. So, whether you know that or not. This is 2 divided by 8 over 10. So that's the same as 2 times 10 divided by 8. So if we graph that, does that look like a tangent? No, it does not look like a tangent. It's tough to tell. It is tough to tell right there, isn't it? But a tangent probably should be, it should look a little bit more like this one, right? Okay, so obviously our slope of 2 is way too much. So this is not a real accurate, it's not a real accurate graph here. But it is really tough to draw a tangent line at this point, isn't it? Because, that tangent, kind of comes to kind of what, and then it bends back over again. So that's a good attempt, but in reality, when we graph that, it doesn't look very good, does it? Not quite right. Oops. I want to do that part. So, what do you guys think? What should we try? Here's 0. Here is, this line right here, which would be, a little bit less than 1. Somewhere up here, let's try that second line. Let's try it as just x. As 1x. And let's see. Ooh, that looks much better, doesn't it? That looks much, much better. Okay? So that is our tangent line. It is. It's y equals x. That's the tangent line. So on your calculator, you can actually find out what the derivative is at a certain point. If we did second function value, and let's say we want to get 0. So 0, 0. Now, if I did second function calculate, and down here option number 6 is dy dx, which of course is Leibniz notation for derivative, right? So if you hit 6, it does go away from 0 here, but that's pretty much as close as the calculator seemingly can get for this operation. And you hit enter, then the derivative shows up there, and this one is 0.99921634. So at 0, the derivative is going to be pretty close to 1. So with that derivative of 1, right, again, I'm just drawing bad tangent lines here. The derivative, okay, so the derivative here at this point is y equals 1. So we're going to put the point at y equals 1. The derivative is actually 1, but getting the calculator to get 1, that's what I'm saying. The calculator runs through a specific algorithm, and it's running, this is an infinite number of single points. So sometimes another time it might get a different number, actually. But this is pretty much as close to 1 as that calculator can get. So that's going to be 1. Here, at this point, because this is sort of a periodic, it's symmetrical, right? This is going to be what for a slope? Yeah, that's going to be negative 1. So we'll go back to this. Negative 1 is going to be that point. Okay, so what have we got so far? We've got blue, 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 dot here, dot here. All right. What about pi over 4? So if we go second function, let's try this way, 6, and then we go pi over 4. Well, let's put in pi divided by 4 to be as exact as possible. the derivative here, that makes sense, 0.707, it's going to be, yeah, that's right here, so pi over 4, this derivative here, alright, is going to be 0.707, so right here, and then this derivative over here, right, is going to be negative 0.707. And if you put all these pieces together, use the symmetry, use your things like that, look at what you get. You get this right here. Right? And if we continue that, this is going to be 1, say like that. Alright, so what do you see here? What do you see? This is the sine graph, 1 period of the sine. And this is 1 period of the derivative of sine. What does that look like? This is, yeah, you guys all know this. This is cos theta. So the derivative of sine theta is cosine theta. So d over dx sine theta. Oh, I guess I got to put x there. I did x. Of sine x is cos x. Okay. So that's going to be helpful when we're taking the derivative of sine functions to know what the derivative is. And in this case, pretty straightforward. The derivative of sine is cos. Now I want you to take a minute and I want you to graph cos. I want you to graph the derivative of cosine. Okay. So here's the cos graph. Oh, I just did that wrong. So here's the cos graph, and look like this. So transfer the derivatives to another graph and see what you end up getting. Okay. So there's cos. Graph the derivative of cos. Alright, so again what you want to do is you want to spot your derivative lines. Okay, where is the derivative 0, where is it positive and negative 1, and plot those lines, and then you can translate that. So if you look down here, this is sort of what it looks like for the first period of cos. And what does this look like? Yeah, it looks like a sine graph that's been flipped upside down, and so you have this. And of course this would continue on forever and ever, both directions. All we need to look at is 1 period. So the derivative of cos is negative sine, and the derivative of sine is cos. So that's going to be huge going forward here. Okay, understanding those derivatives. And we'll do a couple questions where we'll need to use those. Okay, so this is our example we're going to work with here. Find the derivative of sine of 3x. What we have to remember here, and I don't know if you've forgotten this or not, but this is not a multiplication of two things? Remember that? It's not. As a matter of fact, this instead is an outside function and an inside function. So you see sine of 3x as sort of the outside function, and then 3x is the inner function. Okay? So if 3x equals w, you'd have sine of w, just sine of one thing. So we have two separate things. We have the sine function and we have the 3x function. And it's a composite function. Does everyone see that? So what rule do we have to do when we find derivative of a composite function? So which? Chain rule. Exactly. All right, so y prime, or d over dx, is, so what's the derivative of sine of 3x? Positive cos of 3x. So again, in the chain rule, yeah, you do not touch the inside function in the first step, right? So it's, you change the outside. Sine goes to cos. We just learned that. And then in the chain rule, what do you do with the second function? You multiply by its derivative, right? Which is 3. So your answer, the way you'd write it, is 3 cos 3x. Usually you put the number in the front there like that. All right? So that's the, yeah, that's the derivative there. Questions? If you have this as the question, then you can just circle this as the answer. That's fine, as long as you can connect, what this is. As long as it's clear that what this is the derivative of sine of 3x. All right, let's do, how about this one? Y equals x squared cos x. Find y prime. Well, y prime is going to equal the derivative of this. Now this is, what is this? Is this a composite function? Is this, obviously it's not addition of functions, but it's a product, right? So we have function 1 and then function 2. And because this is x, we don't really have another inside function we have to worry about, because the derivative of x is just 1, so we multiply by 1, it doesn't change anything. All right, so when we multiply, we've got to remember to do the product rule. And that is the derivative of the first times the second plus that first term times the derivative of the second. And what's the derivative of cos again? Negative sine. Yeah, negative sine. And so if we simplify this, we get 2x cos x minus x squared sine x. And if you wanted to factor, which would probably be a good idea to factor these expressions, if you can see an obvious factor, we can take an x out, right? There's an x in each. You can't take this x out, remember, because it's not cos times x. So you have to leave that one alone. But you could go this far, I guess. Okay? So at this point, I wouldn't be too worried about if you just left it in this format, but I'm just saying that's what you could do. Good idea to factor, right? Okay. Does that make sense? Everyone okay with all that? For the answer, yeah, right here. That's your answer. Okay. What about what about y double prime for this one? Y double prime, remember we take the derivative of the derivative. So what's y double prime for this one? Let's take a look at this. Well, we have two things going on here. We have a product here, we have a sum, another product. So we'll do product rule here. What do you get? 2x times cos x, the derivative of the first, times the second, plus the first times the derivative of the second, and then minus, for this minus right here, the derivative of the first times the second plus the first times the derivative of the second. Sorry, does that look right? So if we simplified this to cos x minus 2x sine x minus 2x sine x minus, if you distribute that negative sign here in the brackets is nice, x squared cos x. And if there's anything in all four of these terms to take out, then you can do that, but you can just kind of leave it like that too. The 2x sine x's, yeah, I guess you can. Yeah, minus 2x sine x minus another 2x. So you could write that as minus 4x sine x. Yeah, that's the catch. You could do that. That'd be fine. Again, simplification, depending on why you're simplifying, you know, more simplification you might need to factor this eventually, right? If you're going to do concavity, if you find concavity and stuff. But yeah, that's an easy one. It's a good catch there. Sine x minus x squared cos x. Okay. Any other questions? I should point out that when you see this, okay, a negative 2 here, and it's x cubed, I believe, and they're asking you to find the derivative. So first of all, this negative 2 right here, this is the same as this. Okay? That number right there is the same as outside of the brackets, the whole thing. So that means the whole sine of x cubed is all taken to the power of negative 2. The reason why they don't have the numbers there is because it gets confusing if they put the numbers here. Then it looks like, well, is this negative 2 attached to the x, or is it attached to the sine, or what? So that's why they do that. Okay, you can write it. You don't have to write like that, of course, but you could do 1 over sine x cubed all squared. That might be easier for you to see what to do with the chain rule, right? Or if you write it like this, cubed all to the negative 2. You can do chain rule here, right? So negative 2 sine x cubed to the power of negative 3 times, now we got, there's a few layers here. No, we haven't touched the sine yet, you see. So what's the derivative of sine? Cos x cubed. Now what's the derivative of x cubed? 3x squared. So basically here is your differentiation right here. There's your first step of that one. Then you simplify from there. So what would that be? A negative 6x squared times cos x cubed all over sine to the negative 3x cubed, or sine to the positive 3, I should say. So you might want to still write your exponents in positive form, right? So that would bring this down to the bottom, and you write your 3 in between here. So yeah, there are a couple things there too that you should be aware of, those negatives there.